Astronomers have found some really wacky stuff in our universe. Among the weirdest and most extreme objects out there are neutron stars. When a massive star dies, it goes out with a supernova. If that star is 8 to 15 times bigger than our Sun, a neutron star is born in its wake. To understand why, we have to deep dive into a supernova. Stars depend on a balance between gravity pushing in and fusion pushing out. The pressure at a star's core causes hydrogen to fuse into helium, and so on until iron is reached. Up until this point, the fusion reactions release energy and keep the star stable. But at iron, the fusion reaction doesn't release enough energy to oppose gravity, and the star experiences a gravitational collapse. As the implosion reaches the core, let's look at the elementary particles. I'm going to talk about a little something called the Pauli exclusion principle, which basically means that quantum particles don't like being in the same place as each other. A lot of energy is required to force them together. The gravity of the collapsing star is just enough to force protons and electrons into each other, turning them into neutrons. After the core is mostly neutrons, the collapse stops because the star's gravity isn't enough to force neutrons into each other. This is the Pauli exclusion principle coming into play through neutron degeneracy pressure. To understand how extreme this is, imagine an atom the size of a football field. Normally, the nucleus would be like a little marble in the center with even tinier electrons around the field. In a neutron star, the field is packed with neutrons. This makes neutron stars one of the densest objects in the universe. If its parent star was any heavier, it could have forced neutrons into each other and a black hole could have been born. Next, the outer layers of the star bounce off of the core in a massive explosion. All that's left after this is a new neutron star, an incredibly dense ball of neutrons in a state called a superfluid. Physicists believe that neutron stars have layers characterized by different organizations of neutrons. For whatever reason, they've named most of these layers after pasta. The exact properties of this space pasta isn't quite clear, but we do know it's the strongest material in the universe. Post-supernova, the newly formed neutron star retains the angular momentum of its parent star. Angular momentum can be best explained visually. By leaning back, I can go slower, but without touching the ground at all, I can go faster just by making myself smaller. Exactly the same thing happens with a neutron star. Its parent can take months to spin on its axis, while a neutron star can spin many times per second. This is because the parent can be millions of kilometers wide, while the neutron star is just 20 kilometers wide. A neutron star's rapid spin and incredibly strong magnetic field creates pulsars, powerful beams of electromagnetic radiation that's ejected out of each magnetic pole. To a distant observer, they appear as blinking lights because we can only see them if they point at us. These fascinating objects have many more secrets to reveal, and you could be the one to discover them.